Kruskal's algorithm, one of the key algorithms for finding a minimum spanning tree in graphs. By the end of this video, you will know the concept step by step working, and we will also slow example together. First, let's understand what a minimum spanning tree or MST actually means. If you have a graph, basically a network of points, vertices, connected by lines, edges with weights, and MST connects all the vertices using the least total weight possible and without forming any cycles. In real life, this weight could mean distance, cost, or time. For example, in Design the Road network, we want all cities connected with the least total load, length, and without extra loops. Two popular algorithms can do this: Kruskal's algorithm and Prim's algorithm. Today we are focusing only Kruskal's algorithm. Kruskal's algorithm is a greedy algorithm, which means it always picks the smallest available option at each step, hoping to reach the optimal solution. It works on any weighted undirected graph and builds the MST by starting with no edges and adding them one by one, always choosing the smallest weight edge that doesn't form a cycle. The algorithm stops when we have exactly v-1 edges in the tree, where v is the number of vertices. So, step 1, process edges. Before starting, we clean up our graph. First, remove self-loops, edges that connect a vertex to itself. Second, remove parallel edges, multiple edges between the same two vertices, and keep only the one with the smallest weight. This makes sure our algorithm works on a clean, minimal set of edges. Step 2, sort edges by weight. Next, we sort all edges from smallest weight to largest. Sorting is important because Kruskal is greedy. It always tries to add the smallest edge available first. This step takes 0 time, where E is the number of edges. Step 3, build the minimum spanning tree. Now comes the actual MST construction. Starting with no edges, we go through the sorted edge list. For each edge, check if adding it would form a cycle. If it won't form a cycle, add it to the MST. If it would form a cycle, skip it. We use a disjoint set union or ununion point structure for cycle detection. This helps us know if two vertices are already in the same connected component. Now we are going to example problem 1. Let's slow our first example. Step 1, remove self-loops and parallel edges. So this example, no self-loops or parallel edges. Then we go to step 2, sort edges by weight. Step 3, start adding edges. Add smallest edge, check for cycle. If no cycle, keep it. Repeat until we have v-1 edges. Okay, here's our example graph. We have already sorted the edges by weight, smallest to largest. We will go through this list and build the MST using Kruskal's rule. Pick the smallest edge that does not make a cycle. We stop when we have v-1 edges. Here 6 edges, no? So we need 5 edges. First edge EF with weight 1, the smallest. No cycle possible because both E and F were separate. So we add EF. Now E and F are connected. Component EF. Next is ED weight 2. E is already in EF. D is separate. adding ed connects d into that component. So we add ed. Now EFD is one component. Edge AC with weight 3 connects A and C. Both are new to existing components. So we add AC and form AC. AB weight 5. A is in AC, B is alone. So adding AB merge B into that group. Now ACB is one component. We currently have 4 edges added: EF, ED, AC, AB. Actually 4 edges so far. BC with weight 6. Notice B and C are already connected via A. We have AB and AC. Adding BC would make a cycle, so we skip BC. FD weight 6. F and D are already connected through EF and ED. So FD would make a cycle in that component, so we skip FD too. Next, CE weight 7. C is in ABC and E is in DEF, different component. So adding CE joins those two components, and now all vertices are connected in one component. After this, we have 5 edges: EF, ED, AC, AP, CE. That's V minus 1 edges, so we stop. We don't need to consider BD or BE because the MST is complete once we had 5 edges. The MST edges are EF, ED, AC, AB and CE. The total MST weight is 1 plus 2 plus 3 plus 5 plus 7 equals 18. That's the minimum total cost that connects all vertices without cycles. So Kruskal just sort and picks the smaller stages that don't create a cycle. Skipping an edge means its endpoints were already connected. Adding it would be redundant. Alright, here's example 2. This one's for you to try on your own. Follow the same steps we just did. Remove any self loops, list all edges and sort by weight. Pick the smallest edge that doesn't form a cycle. Skip any edge that makes a cycle. Stop when you have V minus 1 edges. Work through it step by step and see if you can find the MST and total weight. If you want me to walk through the full solution in another video, drop a comment below saying do example 2 and I will cover in detail next time. Now we will walk through a complete Java implementation of Kruskal's algorithm. I will explain every line, show a dry run with the graph and run the code so you see the final MST. Let's jump in. Here's the full program we will explain. Big picture. We store edges, remove self loops and parallel edges when adding, sort edges by weight and use union find to avoid cycles while building the MST. After the walkthrough, we will run the program and inspect the output. Int src test weight. This store the two endpoints and the edge weight. Constructor publish int src int test int weight. Simple constructor sets the fields. Next method compare to returns this weight other weight. So Java can sort edges by weight ascending using collections.sort. Easy and important. Kruskal needs the edges in increasing order. Next, public class Kruskal algorithm. V is the number of vertices. Edges is an array list sorting all edges we have added. The constructor just sets V. Later we will add edges with add edge. Next, public void add edge block. So src equals dest return. This ignores self loops and edge from a vertex to itself doesn't help a spanning tree. Next, this loop checks for parallel edges between the same two vertices. If we find one, we keep the smaller weight h by updating e.weight equals weight if the new one is lighter and then return. If not a self loop or parallel duplicate, we add the new edge. This is a simple way to clean the graph while building it. Not scanning edges is 0 per add, fine for demo graphs. But for very large graphs, you might want to hash map key by min uv, max uv to deduct faster. If parent I not equal I, parent I equal find parent I, return parent I. Find return the representative of the set that I belongs to. The key trick here is path compression. During the recursive find, we set parent I directly to the root, flattening the tree. That makes later finds very fast. Path compression means repeated finds become nearly zero. This is what makes union find efficient. First show int root x equals find parent x. Int root y equal find parent y. We get the root representatives for two nodes. Rank is an estimate of tree height. We attach the shorter tree under the taller tree, so the resulting tree is balanced. If ranks are equal, attach one to the other and increment the rank. List H, MST equals new array list. List that will hold MST edges. Collections.sort edges. Sort edges by ascending weight using the compare to we find earlier. Sorting is the dominant cost. Initialize each vertex to be in its own set. Parent I equals I. Ranks start at 0. For every edge from smallest weight to highest, we find the set of its endpoints. If they are in different sets, add in that edge born from a cycle. So we add it to MST and union their sets. So once we have v minus 1 edges, that's a full spanning tree. Finally, we print edges in the MST and compute the total weight. This is what we will check in the console to confirm correctness. These lines define the example graph of 5 vertices. This is ignored because added checks src equals test. This updates the existing edge between 1 and 4 from weight 5 to 4. Nice to show how duplicates are handled. Now I will compile and run the program. Watch the console output. It should list the MST edges and total weight 15. Sorting is 0. Union find operations are almost constant with path compression giving total complicity roughly 0. So that's Kruskal's algorithm. It's greedy, works by sorting edges and adding them carefully to avoid cycles. stops when you have v minus 1 edges. This is very efficient for sparse graphs. For denser graphs, sometimes Prim's algorithm is preferred. If this helped you, give it a like, subscribe for more data structures videos, and let me know in the comments which algorithm you want next. Thanks for watching and happy coding.